This is the third lecture on Legendre differential equation. In the previous one, in the previous lecture we have seen that if we choose alpha is equal to L into L plus 1, then one of the solution of the Legendre differential equation is a polynomial called the Legendre polynomial, and the other one is an infinite series called the Legendre function of second kind. So for a given L, alpha is equal to L plus 1 for a given N, YL of x can be written as ALPL of x plus BLQL of x. And using the recurrence relation, we have found out an expression for the PL of x. In the last class, we have obtained an expression that this is PL k is equal to 0 to n capital N minus 1 to the power k 2L minus 2k factorial to the power L k factorial L minus k factorial L minus 2k factorial to the power x to the power L minus 2k. So that much we have done, and we use this expression to find out P0 is equal to 1, P1 is equal to x, and P2 is equal to half into 3x square minus 1. Now today we shall discuss Rodrigues formula. Rodrigues formula is actually expresses a special function of a particular order. By special function we mean Legendre polynomial, Harmonic polynomial, Logar polynomial, or Bessel function. And there are others too. These are included in your syllabus. So Rodrigues formula expresses a special function as the derivative of a known function. Say for example, PL of x is related to DL dx L of x square minus 1 to the power L. By known function we mean this. This is a known function whose Lth derivative gives you PL. There is some constant that we shall derive. So this is the spirit of Rodrigues formula, and it is very helpful for determining special function of lower orders. So we start with this. V of x is equal to V0 of x is equal to x square minus 1 to the power L. Now we define V1 is equal to dv dx is equal to twice Lx x square minus 1 to the power L minus 1. We multiply both the side by x square minus 1, so we get x square minus 1 times V1 is equal to twice Lx V0. Now we differentiate this L plus 1 time. L plus 1 time successive differentiation using Leibniz rule. Leibniz rule is applicable when we have a function which is product of two functions. Let f of x is equal to g of x times h of x. You need to calculate fn of x. That is the nth derivative dn dx n of f. This is fn. Then Leibniz rule says that this is summation over k is equal to 0 to n nck gk of x h n minus k of x. It could also be written, the order may be interchanged. This can also be written as nck g to the power n minus k, this is the derivative, and h, anything you can use. This is the Leibniz rule. This is Leibniz rule. I hope you are aware of it. So if we use Leibniz rule, you see that this function, it's for the function itself is x square minus 1. First derivative is 2x, second derivative is 2, and the higher derivatives are 0. So if we apply Leibniz, so this is x square minus 1. This is bl plus 2 because we are differentiating it l plus 1 times. So l plus 1 will be added to v1. Then l plus 1 c1, and if we differentiate this, this is 2x and this is b of l plus 1. Then for the second term, l plus 1 c2, its the second derivative is simply 2, and this is bl. Now coming to the right hand side, 2l is taken common. First is x, bl plus 1, then l plus 1 c1, the derivative of x is 1, and this is bl. All other terms are 0. Now coming to this term, this is x square minus 1 b of l plus 2. Coming to this term, this is 2 l plus 1. L plus 1 comes from l plus 1 c1, x bl plus 1. Here we have this l plus 1 c2 is l into l plus 1 by 2. These 2 cancels with this, so we have l into l plus 1 bl. Now the right hand side, 2lx v of l plus 1. This term, l into l plus 1, bl. Now you see that these two terms, 2lx cancels out, so this term is left with 2x. On adjustment, this is plus 2x bl plus 1, and this, sorry, here we have 2 terms because it is 1, so 2 is there. So this is l into l plus 1 bl is equal to 0. There is the adjustment. Or we write 1 minus x square bl plus 2 minus 2x bl plus 1 plus l into l plus 1 bl is equal to 0. Compare it with Legendre differential equation of Legendre the differential equation that Legendre polynomial satisfies. PL double prime minus 2x PL prime plus L into L plus 1 PL of x is equal to 0. Here we write, you know that PL is equal to DL dx L of V0, that is DL dx L of then. So this is actually, this equation we can also write as like this. VL double prime minus twice x VL prime plus L into L plus 1 VL is equal to 0. What does it mean? It means that PL is actually related to PL, that these two equation indicates that PL is related to VLs with some constant. Now this if we write explicitly, this is C dl dxl x square minus 1 to the power L. Now we require to find out the constant, multiplicative constant. Again we shall use Leibniz, but first let me define some. We write PL of x is equal to C VL of x is equal to C where D operator is ddx operator. We write it as C d to the power L operating on A0 B0, where we define A0 to be x plus 1 to the power L and B0 to be x minus 1 to the power L. Now what is the A1, the first derivative? First derivative is L x plus 1 to the power L minus 1. A2, L into L minus 1 x plus 1 to the power L minus 2. Going in this way, AL is equal to factorial L. Now coming to BL part. B1 is equal to L into x minus 1 to the power L minus 1. B2 is equal to L into L minus 1. X minus 1 to the power L minus 2. Going in this way, BL is equal to factorial L. Now you see that at x is equal to 1, all the b's except BL are 0. At x is equal to 1, BL is equal to factorial L and all other BKs are 0. And so if we write this one, if we PL is equal to C, then we write this as BK, and we define we set PL of 1 is equal to 1. This is a very important property of Legendre polynomial. So if we apply it at L is equal to 1, we see that this is PL of 1 is equal to 1, and on the right hand side we have C, and if we expand this, then we find that only BL is non-zero and all others are 0. So we write C times A0 at x is equal to 1 times BL at x is equal to 1. So this is C. A0 at x is equal to 1 is 2 to the power L, and this is L factorial. So we find that C is equal to 1 over 2 to the power L factorial. So which completes the Rodrigues formula, that PL of x is equal to 1 upon 2 to the power L factorial L dl dxl of x square minus 1 to the power L. So this is the Rodrigues formula, that what we propose, that the special function Legendre polynomial of order L is obtained as the Lth derivative of this function. Let me apply this to few to calculate, let me express this Rodrigues formula for the calculation of Legendre polynomial of few lower orders. So the Rodrigues formula is PL of x is equal to 1 upon 2 to the power L factorial L dl dxl x square minus 1 to the power L. This is the summary that we have done all through. Now coming to P0. So for L is equal to 0, we have P0 of x is equal to 1 upon 2 to the power 0 factorial, and this is not a differentiation at all. So this is 1, this is 1, so it is 1. L is equal to 1. 2 to the power 1 factorial ddx of x square minus 1 to the power 1. So this part is half, simply half, and when we differentiate, so this is ddx of x square minus 1, so this is 2x, so altogether it is x. Two factorial first, this is 4 times 2, this is 8. The numerical factor is 1 upon 8. Now this is, once we differentiate it, we have 2x square minus 1 times 2x. So this is 4, so it is half ddx operating on x times x square minus 1, half, this is x square minus 1, and when we differentiate this, it is 2x square, so altogether it is half 3x square minus 1 as we obtained earlier. So that's why Rodrigues formula enables us to find out the special function of lower orders. And the higher orders special function can also be expressed, obtained from this formula, but the labor will be too much. Now earlier we have obtained an expression for the Legendre polynomial starting from the recurrence relation. Now we shall apply this one to find out an expression for the Legendre polynomial. Let me obtain the series of Legendre polynomials starting from Rodrigues formula. So we have PL of x is equal to 1 upon 2 to the power L factorial. We just, to shorten the notation, we use this, and for this one we write summation over k is equal to 0 to L LCK minus 1 to the power k x square to the power L minus k. So this is equal to 1 upon 2 to the power L factorial summation over k is equal to 0 to L minus 1 to the power k dl operating on x to the power 2L minus 2k. Now d operating on x to the power 2L minus 2k is equal to 2L minus 2k x to the power 2L minus 2k minus 1. D square operating on if we use 3 so if we go on such way, so dl operating on the factor will be 12 minus 2k 12 minus 2k minus 1 going right. For 3 it is minus 2, so for L it is minus L plus 1 and x to the power 2L minus 2k minus L. So this part is no, for 2 it is minus 1, so 1 minus, so minus L makes it this and this is this part can be written as 2L minus 2k factorial, then the rest of the term L minus 2k factorial x to the power L minus 2k. So when we use this, we have missed LCK, where LCK is factorial L factorial k L minus k factorial. This L factorial goes, so we have to the power L in the numerator. We will have, and the x in numerator we have 12 minus 2k factorial, denominator we have k factorial L minus k factorial L minus 2k factorial x to the power L minus 2k. Now the question is that k ranges from 0 to L as we obtained from the binomial series, but coming to this term, if k 2k is greater than L, all this factorial will be undefined, so those terms will be omitted. So k does not run up to L, but it runs up to capital N, where capital N has been defined earlier. So it gives you the same expression as the Legendre polynomial as we have obtained earlier. In the next class, we shall discuss the generating function of Legendre polynomial. And before going to the generating function that will be taken up in the next class, today we shall use a bit of homework. We shall perform a bit of homework, that is, we shall consider a the binomial expansion of a particular kind that will be helpful in discussing the generating function. We consider a function f of x is equal to 1 minus x to the power alpha, where alpha may be any real quantity. We want to expand it in Maclaurin series. In Maclaurin series, it is given as summation over k is equal to 0 to infinity x to the power k factorial k fk at 0, where fk is the kth derivative of the function evaluated at x is equal to 0. This is x to the power k. So we consider this function k fk at x and fk at 0, where the function is this one. So when k is equal to 0, it is 1, it is 1. K is equal to 1, this is alpha 1 minus x, this is minus alpha. Second derivative, which is plus alpha into alpha minus 1, 1 minus x to the power alpha minus 2, and this is plus alpha into alpha minus 1. Third derivative, minus alpha, alpha minus 1, alpha minus 2, 1 minus x to the power alpha minus 3. So this is minus alpha into alpha minus 1 into alpha minus 2. Going in this way, we can this is minus 1 to the power k. So the Maclaurin series, this expansion is factorial k and then this part. Let us consider a special case. Let alpha is equal to minus half, in which case we have 1 minus x to the power minus half is equal to Now coming to this part, minus of, then this is minus 3 by 2, this term is minus 5 by 2, this term is this minus half minus k plus 1. So this is, if we take it can be written as minus k plus half. So this is taken half common, minus 2k plus 1. So there are k such term. If we take k out, the denominator is 2 to the power k, and there will be minus 1 to the power k, so which makes it is k to minus 1 to the power 2k, which is positive, and we will have 1 3 5 right up to 2k minus 1, this part. Now we can write it as minus 1 to the power k, and we adjust, we write 2 4 6 up to 2k. So this becomes 1 2 3 4 5 2k minus 1 times 2k. So we have to adjust this. Earlier we have 2 to the power k, and then we write 2 4 6 right up to 2k. So there are k such terms, so it will be 2 to the power 2k minus 1 to the power k, the denominator 2 to the power 2k k factorial, and on the numerator we have 2k factorial. So if we write this, you see that there is a factor minus 1 to the power k, this which is positive always. So we have summation over k x to the power k factorial k x to the power factor, and then we have 2k factorial and 2 to the power 2k k factorial. Altogether this is summation over k is equal to 0 to infinity 2k factorial 2 to the power 2k k factorial square times x to the power k. This is a very important relation which we shall use in the next class while discussing the generating function. So let me write the conclusion that the conclusion is that 1 minus x to the power half 1 minus x to the power minus half is equal to summation over k is equal to 0 to infinity 2k factorial 2 to the power 2k k factorial square x to the power k, and this expansion is valid when mod x is less than equal to 1, which we know from the analysis of the remainder term in Maclaurin series. This much for today. In the next class we shall consider this expression to discuss the generating function. The generating function is a function which contains the argument x of PL and a parameter x of the PL x and a parameter, and the generating function is expanded and as a convergent infinite series in powers of the parameter t and multiplied by the special function of the same order, that is t to the power L is multiplied with PL of x, and if we equate the left hand side and right hand side we can get the special function of a definite order from this. This generating function is very suitable for finding out the special function of higher order, where the Rodrigues formula or the series expansion may become very much tedious or laborious, in which case the expansion method or the generating function method is found to be very helpful.